Multi-loop circuits. We have already studied single loop circuit, and we have mentioned the loop rule or Kirchhoff voltage law, and we have said that in Kirchhoff voltage law, in a complete loop, the voltage or the summation of the potential difference for the complete loop equals 0. The question now is, what will be the situation if we have multi-loops? We have different loops connect to each other. If we have different loops connect to each other, there will be a junction between the loops. So, for example, we have first loop here connecting R1, R3, and E1, and a second loop connecting R3, R2, and E2, and the first loop is connected to the second loop through two junctions, the point B and the point D. So there is another rule called junction rule, and in junction rule it says that the sum of the currents entering any junction must be equal to the sum of the current leaving the junction. Actually, we have studied something similar in the current. Do you remember it? So this rule is often called a Kirchhoff junction rule or Kirchhoff current rule. For example, if we are talking about here, we have I2. I2 is coming from point D to C to B. And we have I1 is coming from B to A to D. And we have I3 coming from B to D. So in this case, the point D, the currents I3 and I1 enters the point D. And the current I2 leaves the point D. So in this case, I2 equals I3 plus I1. On the other hand, if you are talking about the point B or the junction B, the current I2 enters junction B, while currents I1 and I3 are leaving junction B. So the currents enter the junction B must equal the currents leaving the junction B. So I2 equals I3 plus I2. So that's what we are seeing. The left hand loop in counterclockwise direction from point B. The left hand loop, this left hand loop, starting from B and counterclockwise. So we are moving like this. If we apply Kirchhoff voltage law, so we have the potential E1 and we are going in the same direction, so E1 will be positive. We have the voltage drop across resistance R1 and the current here in the same opposite direction of the loop, so it is minus I1 R1. And finally R3 multiplied by I3, but in this case the current is in opposite direction to the loop. So in this case it is plus I3 multiplied by R3. So the first loop is E1 minus I1 multiplied by R1 plus I3 multiplied by R3 equals. The right hand loop also in counterclockwise. The right hand loop in counterclockwise like this. If we have applied Kirchhoff voltage law, we can say that minus E2 minus I3 multiplied by R3, because the loop is the same direction of the current. So minus I3 multiplied by R3 minus I2 multiplied by R2. So everything is minus here. So minus I3 multiplied by R3 minus I2 multiplied by R2 minus E2 equals 0. Now we have three unknowns, I1, I2, and I3. And we have only two equations. So we cannot solve three unknowns by using only two equations. So we need another equation. The other equation is obtained by Kirchhoff current law. The current I3 plus the current I1 must equal the current I2 because of the junction B. Or in other words, the current I2 inside junction B must equal the current I1 by plus I3. So both cases, if I'm talking about junction B or junction D, I obtain the same equation. Now I have three equations and three unknowns. We can solve these three equations to find out the unknowns I1. Okay. What will be the case if you are talking about resistances in parallel? Resistance in parallel, it means that the resistance are directly wired together on one side and directly wired together on the other side. What this means? If I'm assuming this resistance R1 and this is a terminal 1 and this terminal 2 of resistance 1, and here resistance 2, this terminal 1 and resistance 2, terminal resistance, and resistance 3, terminal 1, terminal 2. We can see that in parallel combination, the terminal 1 of resistance 1 is connected to terminal 1 of resistance 2 is connected to terminal 1 of resistance 3. And at the same time, terminal 2 of resistance 1 is connected to terminal 2 of resistance 2 connected to terminal 2 of resistance 3. So that's what we are saying. Parallel means that the resistance are directly wired together on one side and directly wired together on the other side. And then the potential difference V is applied across the pair of connected sides. So the potential difference is connected between this pair, this terminal 1, terminal 2, terminal 1. So the voltage is applied between these two terminals. Thus, all three resistances have the same potential difference V. So in this case, this potential has the potential difference between the point A and B. This potential has this potential difference between point A and B because actually A is all this point and B is all this point. Okay? Thus, all three resistances have the same potential difference V across them, reducing current through each one. Okay. Before going on, let's agree on that it is not mandatory to find out the resistance parallel geometrically like this. This actually parallel resistances and also it is parallel in geometry. But actually, for example, if this resistor was horizontal, for example, this direction, for example, and connected by a wire from this point to reach to this point. So effectively, this is the same as it is vertical and this point is connected directly to this point. So the main idea of parallel resistances is that terminal 1 here connected to terminal 1 here and terminal 2 here is connected to terminal 2. Regardless, terminal 2 geometrically in the same parallel direction or in other direction, but it is electrically connected by equipotential surface or what we are saying short circuit or wire. Okay? Alright. So for the case of resistances in parallel, the current I1 would be V over R1 and the current I2 would be V over R2 and the current I3 would be V over R3. So I1 V over R1, I2 V over R2, I3 V over R3. And by using the junction rule or Kirchhoff current law, we can say that all this point is a node called A, and all this point is a node or a junction called B. So the total current enters the junction A equals the summation of the current leaving the point A. So the total current I, which is coming from the EMF source, equals the total current entering the resistors. So I equals I1 plus I2 plus I3. So in this case, the total current I would be V multiplied by 1 over R1 plus 1 over R2 plus 1 over R3. Now, if you are looking about an equivalent resistance for this parallel combination of these resistors, we can assume that R equivalent will introduce the same current if it has the same potential difference V. So I would equal V equal R equivalent. So for the equivalent resistance, the same current will be introduced. So in this case, this I would equal this I. So in this case, V over R equivalent equal V multiplied by 1 over R1 plus R1 over R2 plus 1 over R2. Or in other words, 1 over R equivalent equal 1 over R1 plus 1 over R2 plus 1 over R3. Or in generally, we can say for n parallel resistance, 1 over R equivalent is the summation of 1 over Rj, where J from 1 to n, where n is a number of parallel resistance. So this is the rule for the equivalent resistance of parallel resistors. For a special case, if we are talking about just two resistors in parallel, we say that 1 over R equivalent equals 1 over R1 plus 1 over R2, which is a special case. We have only two resistors. So by making the denominator the same, we can say 1 over R equivalent is R2 plus R1 over R1 multiplied by R2. So in other words, R equivalent would be R1 multiplied by R2 over R1 plus R2. So this is a simple rule for only two parallel resistance. So for any two parallel resistance, the equivalent resistance is the multiplication of these two resistance over the summation of these two resistances. This special case for two parallel resistance only. Okay, so based on our study, we say that if we have series resistances, the equivalent resistance would be the summation of these resistances, and in this case, the current through all the resistors will be the same. If we are talking about parallel resistances, 1 over R equivalent of the parallel resistance would equal the summation of 1 over R for these parallel resistance. And in this case, the same potential difference across all resistors would be the same. If we remember, for the case of the capacitor, it is the opposite. If we are talking about series capacitors, 1 over C equivalent equal the summation of 1 over C, and in this case, the same charge in all capacitors are the same. And if we are talking about parallel capacitors, in this case, the equivalent C equivalent would be the summation of the values of the capacitor Cj, and the potential difference across all the capacitors would be the same. So please take care between or the difference between the resistance and capacitor in the case of series and parallel. Okay.